Chapter 2. Early Atomic Theory and Early Quantum Theory. 2.1 Introduction. The review of early atomic theory will start with the limits of the classic theory as regards the atom, where classical theory predicts a rapid radiative decay and collapse of all atoms. Since that didn't happen, a new theory was indicated. Better than a predictive failure of the old model is new data to support the new model, and that is what occurred with the observation of spectral lines in hydrogen by Balmer in 1885. Balmer's didn't just see spectral lines. He identified a precise mathematical relation describing their positions that required only one universal constant as fit parameter. This aspect astonished the scientists of the day, for good reason, and led to efforts by Rydberg and Sommerfeld to look at spectral lines and fine-splitting in those lines. What is revealed from the analysis of spectral lines are universal constants, alpha directly, aka the fine structure constant, and Planck's constant indirectly, grouped with alpha in Rydberg's universal spectral constant. Also, in the fine structure splitting, there appears to be quantization according to angular momentum.
The history of the quantum and appearance of Planck's constant is probably more familiar. Quantization on energy change, Planck, 1901. Quantization on energy, photon, Einstein, 1905. Bohr model, Bohr, 1913, and Sommerfeld-Wilson, 1919. Stern-Gerlach experiment, intrinsic spin is revealed, 1922. Wave-particle duality, de Broglie relation, 1923, quantization on matter. Wave-particle duality, Compton effect, 1924, photon-electron scattering. A synthesis of the quantization and wave-particle duality concepts was occurring with the Bohr model in 1913, with refinements in 1919, and with Bohr's recovery of the Rydberg equation, an explanation of the Rydberg constant. In 1923 there was then proposed the correspondence principle. Wave-particle duality was revealed in the results of 1923 and 1924, and the transition to modern quantum theory was about to occur. See Chapter 3 for further details.
2.2 Classical Atomic Theory. The brief history of classical atomic theory starts with Maxwell's unification of the radiation picture, 1855. In 1887 there were three major discoveries, to be discussed next, but only the Michelson-Morley ether experiments, showing no ether for electromagnetic wave propagation, are commonly known. With the discovery of the electron in 1897 by J.J. Thomson, there then followed a discovery of heat structure of the atom. Thomson's original plum-pudding model, 1904, would be superseded by the Rutherford model with use of scattering experimental results, 1911. In this process it was only becoming clearer, however, that there was a fundamental instability in atomic model due to radiative collapse. A simple approximation using the Larmor formula, section 4.2.3, will show that this atomic collapse should happen faster than a nanosecond. So there's clearly a problem with the classical theory.
Maxwell unifies radiation picture, 1855. In 1855 Maxwell read a paper to the Cambridge Philosophical Society titled, On Faraday's Lines of Force. This was his first presentation of a simplified model of Faraday's work. His work unified electricity and magnetism via a linked set of differential equations. Eventually the work was published more completely in 1861. Hertz's experiments on electromagnetic waves indicates photoelectric effect, 1887. In 1887, while engaged in his famous experiments on electromagnetic waves, Hertz made the initial observation of the photoelectric effect. He found that the length of spark induced in a secondary circuit was reduced when the terminals of the spark gap were shielded from the ultraviolet light emitted from the sparking on the primary circuit. This led the Hertz to perform further experiments and establish 1. Only electrons or minus ions appear to emitted from polished metal plates upon illumination. 2. The electrons, or minus ions, are only emitted if the light is above a threshold frequency.
3. When the current is produced, its magnitude depends on the intensity of the illumination. And 4. The energy of the emitted photoelectrons is independent of the intensity of the light and varied linearly with the frequency of the light. Michelson-Morley experiment on existence of an ether for electromagnetic wave propagation, 1887. Maxwell's theory had indicated propagation of electromagnetic waves with a velocity that of the speed of light as early as 1862, in comments made by Maxwell, and in explorations along these lines in 1887 the experimental question had arisen about whether a medium was necessary or implied by the existence of such waves. If there were such a medium, or ether, it was proposed that the Earth's motion would reveal that ether with any interferometer dialed to cancel waves, maximum interference at detector, and simply wait for motion in that ether to result in the interference being undone, revealing the effect of such an ether. But this ether effect was not observed, ergo no ether.
Michelson-Morley observation of the fine structure in spectral lines, 1887. The fine structure in spectral lines was first observed by Michelson and Morley in 1887. The early Bowie model could not explain these line splittings. It wasn't until Sommerfeld modified the Bohr relation for relativistic effects, similar to those indicated by Einstein's Mercury precession results, that a prediction for the splittings within the Bohr-Sommerfeld model became possible. This is where the constant alpha came into the form that it is known today, alpha 1/137. Electron discovered, J. J. Thomson, 1897. Electrons were first revealed in the form of a cathode ray composed of negatively charged particles that had very small masses, as indicated by a charge-to-mass ratio that was very large. This would be the first subatomic particle discovered.
Thomson model, plum pudding model, with electrons as plums. 1904. In 1904 Thomson put forward his famous plum pudding model where the atom was like a plum pudding with small electrons like plums, stuck, mostly immobilized, in that pudding consisting of a positive background pudding or cloud. We now know the roles are switched, with electrons moving, and instead of a diffuse countercharge background, it is a highly concentrated positive charge at the nucleus. Geiger and Marsden, 1908 to 1909. Before the complete Rutherford-Geiger-Marsden model would be described, a number of scattering experiments would be performed. From this early work the power and utility of scattering experiments would be revealed, the workhorse of the particle physics experimental process. In these efforts the term nucleus was used for the first time.
Rutherford model, 1911. Having identified the constituent positive and minus charged elements, and identifying a positive nucleus together with minus small electron in a form of orbital model, the Rutherford model was obtained. 2.3 The observation of atomic spectra and the beginning of the quantum revolution. The first signs of a break from the classical theory was in the observation of spectral lines from heated gases or vapors. There was nothing in the classical theory to explain this discrete-like phenomenon of emission only at particular spectral lines. It wasn't until Balmer showed an almost miraculous fit on these spectral lines, with only a single fit parameter, that the scientific community became interested. Balmer, 1885. In 1885 Balmer observed the spectral emission lines for hydrogen, and was able to describe the collection of lines with a simple equation involving only one constant. Here is a modern picture of the spectral lines. Figure 2.1. Visible spectrum of hydrogen, from the Wikimedia Commons.
Here is the modern form of Balmer's equation. See the next equation, where lambda is the observed wavelength, B equals 364.50,682 nanometers. M is greater than 2 is the initial state. The red line in the image above has the M equals 3 initial state and produces light at wavelength 656 nanometers. This result, with its simple description with one parameter, did not fit in the classical mechanical description known at that time, yet it obviously was tied to something fundamental in that only one fit parameter was involved. Thus the nature of the constant B became of great interest. Rydberg, 1888. In 1888 Rydberg clarified matters further by providing an equation that would describe all the main spectral lines for hydrogen. See the equation shown.
Where R sub h equals 1.0967758 times 10 to the 7th m to the negative 1 power is the Rydberg constant for hydrogen. In 1890 Rydberg extended his result to all hydrogen-like atoms, having only one electron, with different constant for different atom by replacing R sub h goes to z squared R sub h, where z is the atomic number of the hydrogen-like atom. Looking ahead for a moment, with the simple Bohr model, 1913, and with the modern Schrödinger equation solution we get the same result, describing energy levels that depend on the n appearing before, now considered a principal quantum number, as 1 divided by n squared, and the results are now seen as an energy difference between energy levels that corresponds to the emitted light. The more modern theories then give the same formula as Rydberg, except it is revealed what comprises the Rydberg constant. See the next equation.
Where alpha is alpha, the fine structure constant, h is Planck's constant, m sub e is the mass of the electron, and c is the speed of light. Thus, the Rydberg constant is a surprising collection of the two main quantum constants as well as the speed of light and the mass of electron. Although Planck's constant would not be seen until 1901, the constant alpha had already been seen. As mentioned, in 1887 Michelson and Morley observed the fine structure in the spectral lines for hydrogen, where each line had an energy level splitting according to the level's energy with a factor of Z alpha squared, where alpha approximately equals 1 divided by 137 was an experimentally observed value. The appearance of the number 137 was not given much heed at the time. Sommerfeld, 1919. The first designation of the constant alpha as it is now known.
In the modern quantum theory, the lines splitting on energy levels will have precisely the leading Z alpha squared form indicated by Michelson and Morley. If taking the Schrödinger approach and adding relativistic corrections to lowest order, 1927, there is obtained. See the equation shown. Note, however, that the above result was already obtained in 1919 by Sommerfeld using Bohr theory. It is from Sommerfeld that we have the notation and definition of alpha that we use today. 2.4 The mystery of alpha, see for extensive details.
Sommerfeld noted the almost Kabbalistic underpinnings of the mathematics describing spectral lines, referring to the Rydberg inverse square equation as a Kabbalistic formula in his 1919 paper. In that effort, Sommerfeld updated the Bohr model of hydrogen to explain the relativistic fine splitting in the spectral lines of hydrogen. He obtained a result with a single fit parameter, now called alpha, or written alpha. The value alpha introduced quantified the gap fine structure between spectral lines and, as mentioned, is also known as the fine structure constant for that reason. Oddly, there was nothing Kabbalistic about Rydberg's constant or equation, but there certainly was for the result obtained by Sommerfeld. As noted already, Sommerfeld adopted the notation alpha approximately equals 1 divided by 137 for the fine structure constant, where 137 is an actual Kabbalistic number. So, the mystery deepens. This mystery is explained in where it is seen that a maximum information propagation construct, whether reality through the emanation process Book 7, or simply some form of communication optimization like written language with gematria, will often give rise to the appearance of alpha as a maximum perturbation parameter in some sense.
The obsession with alpha did not stop with Sommerfeld. His famous student, Wolfgang Pauli, was very interested in the origins of alpha as well. In Pauli's Nobel Prize lecture he writes, italics mine, "From the view of logic, my report on exclusion principle and quantum mechanics has no conclusion. I believe it will only be possible to write the conclusion if a theory will be established which will determine the value of the fine structure constant, and will thus explain the atomistic of electric fields actually occurring in nature." Pauli was obsessed with the origins of alpha, so much so that he sought psychological help from the famed psychoanalyst Carl Jung, with whom he eventually partnered to try to solve the mystery of alpha. The madness is contagious. Carl Jung went on to write about archetypes, which were curiously similar to the major arcana as outlined in the tarot. A popular history book describing this odd couple interaction can be found in Arthur Miller's 137.
The obsession with alpha continued with the next generation of great physicists as well, particularly Feynman, who said, "There is a most profound and beautiful question associated with the observed coupling constant, the amplitude for a real electron to emit or absorb a real photon. It is a simple number that has been experimentally determined to be close to 0.0854245. My physicist friends won't recognize this number, because they like to remember it as the inverse of its square. About 137.03597, with about an uncertainty of about 2 in the last decimal place. It has been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number up on their wall and worry about it. Immediately you would like to know where this number for a coupling comes from. Is it related to pi or perhaps to the base of natural logarithms? Nobody knows. It's one of the greatest damn mysteries of physics. A magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. We know what kind of a dance to do experimentally to measure this number very accurately, but we don't know what kind of dance to do on the computer to make this number come out, without putting it in secretly.